Alright guys, welcome back. So today we're going to finish sort of our basic chemistry review with chemical reactions. So when we talk about a chemical reaction, this occurs whenever we have a compound or a set of atoms that are breaking apart and we're forming new products on the other side. So we're rearranging their chemical bonds and making something different out of them. So when we talk about chemical reactions, right, the materials that are initially going into the reaction themselves, we talk about those as those reactants. And those are the molecules or atoms, in which case we've got to pull them apart, so we've got to break their chemical bonds so that we have these individual atoms to work with. We then put them back together in the materials that get created in the chemical reaction known as products. So if we take a look, right, in this particular example, I've got two hydrogens and oxygen. Those are my reactants, those are my starting materials. We break those atoms apart, so these bonds are going to come apart, and we're going to put them back together in some new arrangement. In this case, we're going to make some water out of them. And oftentimes we talk about these chemical equations, these shorthand ways to represent the reaction itself. So writing it out, how many of a particular molecule of a particular compound goes into those reactants and what do I get out as products. And in this case, if I have more than one molecule of a particular compound, so the hydrogen's a molecule in this case, I've got two of them, I've only got one of oxygen, right? If there's no number out front, it's understood to be a 1, and I end up creating 2 molecules of oxygen out of that. Keep in mind, when you look at chemical equations, your arrow or that yielding sign always points to your products, right? So if I were to have flipped this arrow and said water, arrow went this way, oxygen and hydrogen, then these guys would become your products, this would become your reactants. So just be careful with that. Every now and again I've seen that show up on a test question, keystone question, so make sure you're watching where those arrows are pointing, because that's going to tell you the direction in which the equation or the reaction is happening. So what if we're mixing things together in a lab and we want to know whether or not a chemical reaction is actually occurring? Well, there's a bunch of particular indicators we can look for as evidence for a chemical reaction. Temperature change, for example. Does mixing those two materials make the product warmer or colder than what we started with? Light's a great example. Any of you ever play with a glow stick before? Alright, the breaking of that glow stick, you got to pop the inner tube because you're now mixing up chemicals, and that light that's being given off is an indicator that a chemical reaction is happening. Changes in electrical potential. Do I go from a substance that was capable of producing an electrical charge and can no longer do so, or does the opposite happen? Water in and of itself, right, doesn't conduct an electrical charge, but we create salt water, which breaks apart atoms, and now we can. Color change is another example. Think of tarnishing of any sort of metal. It's being oxidized by the oxygen, so it's combining with oxygen in the air. Another example is the Statue of Liberty, same deal. All right, gas formation. If any of you have ever made those lovely baking soda and vinegar volcanoes as kids, that gas formation, that carbon dioxide that's coming off forming those bubbles, is a result of that chemical reaction. Or if you've ever seen a precipitate form, where you get this solid that comes out of a mixture of two liquids. One you can try at home. If you take some milk and some lemon juice and mix it together and let it sit, you'll get this clumping of fat particles and protein particles out of the milk itself. That's a precipitate, and that's because you've got a chemical reaction that's going on. Now, one caveat I want to throw in here to be careful. While this may be an indicator of a chemical reaction, they don't always mean that a chemical reaction is happening. There could be other solutions getting formed, other mixtures happening that can give off some similar results. So it's something we can look for as an indicator, but we really want to make sure we're using some other material or other criteria to make sure that it really is a chemical reaction happening and not something else. But it's at least a place to start. Something else to keep in mind when we talk about chemical reactions is this idea of bond energy. So in order for us to go through a chemical reaction, bonds have to break and then have to reform. And the amount of energy that gets associated with those particular bonds that we're breaking and creating really makes a big difference as to whether or not that chemical reaction is going to happen easily on its own. So anytime I've got a bond that forms, energy is always released, period. I always get energy back when those bonds form. The flip side is also true. I always need energy to break them. Okay? So the question then becomes, what's the difference between the energy I have to put into a chemical reaction to break the bond versus what I get back out when the bond reforms? So there is a connection between the type of bonds we deal with and how much strength is behind them. Covalent bonds in and of themselves tend to be the strongest types of bonds that we form. And then there's going to be variation within those covalent bonds based on the atoms that come together. Ionic tends to be somewhere in the middle, and hydrogen bonds, or those intermolecular bonds that we're going to talk about, those are the weakest. Okay, so the stronger the bond type, the more energy I need to break it. And keep in mind that there is variation within even each of these categories based on the elements that are coming together to make those compounds. Alright, but it at least gives you some idea as to strength. Why does it matter? Well, to go through a chemical reaction, right, I have to break the bonds. I've got to be able to pull the atoms apart in order to make new products. Which means it's going to take energy to do that. And what we talk about is that initial energy that is required to break the bonds in the reactant and get that reaction rolling is something called activation energy. And every chemical reaction needs to meet a certain amount of energy put in so that the particles collide hard enough to break the bonds. If I never reach that minimum amount of energy input, the bonds never fully break and the reaction never actually happens. So the question then becomes, well, how much activation energy do I need to put in to get that reaction to start, as opposed to the energy that I get back out when my products form? And that's where we talk about the difference between an exothermic or exergonic reaction and an endothermic or endergonic reaction. I threw both terms up here, exothermic and exergonic. And exothermic specifically is referring to heat, although it typically is what gets used more commonly. Exergonic is a little more specific to just talking energy in general, so just in case you see either term, I wanted to throw them up there so you would understand that essentially they're the same thing. They're describing the same kind of chemical reaction in which I'm going to absorb a certain amount of activation energy, but the energy that I get back in my products is actually more. And so I end up with excess energy on the back end. And so you'll typically see these reaction graphs. So here's my reactants. Okay. From here to here is my peak of activation energy, and maybe it's a good idea for you to label this in your notes. So this is the maximum amount of energy, or my activation energy, that I need in order to break the bonds in my reactants. From here to here, however, is the energy that I get released, and maybe, again, not a bad thing to label in your notes. So when we look at classifying chemical reactions as exothermic or endothermic, the question really becomes, what is my net difference in the amount of energy I had to put in versus the amount of energy I got back? So in this case, pretty small amount of investment and a really big payoff, and so I end up with, for lack of a better analogy, I end up with a net profit. Think of it like running a business. Alright, maybe I had to put in $100 to get that initial product, but I was able to turn around and sell it for $200. And so I ended up netting a $100 profit. That's what's happening in these types of chemical reactions. And so these kinds of reactions tend to happen spontaneously, they tend to be quick, easy to get started, easy to finish. A lot of times that excess energy, if it doesn't have anywhere to go, will come off as heat or light. So something like the glow stick reaction is an exothermic exergonic reaction. We're getting excess energy coming out of that chemical reaction, and we see it as the light in the glow stick. Some other examples that are happening in nature: bioluminescence. Alright, where we actually get glowing organisms. Alright, and so they've got these chemical reactions that are happening as part of their metabolism, and they end up glowing because they make this excess energy and it's got to go somewhere and it comes off as light. And a lot of times it's bacteria, and so they're using it as being part of a symbiotic relationship. If you've ever seen Finding Nemo, we're talking the anglerfish. He's got the little dangly thing right in front of his head, right? It glows in the dark. And it's not the fish itself who's actually doing the bioluminescence, but there's bacteria that live in that structure symbiotically. They go through their metabolism, they happen to make lots of excess energy, and it comes off as light. We'll also talk about cellular respiration this year, and that's an exothermic reaction as well. It gives off lots of heat, but also gives off lots of energy. And it's actually what your body does every time you eat. So you take in that food, we break it down into smaller chunks, and then your body is able to use that excess energy for other processes in your body. The opposite to this then is your endothermic or endergonic types of reactions. And a lot of metabolism processes are in fact endothermic. Photosynthesis is just one example where I've got to absorb all of this energy from somewhere, but I don't really get crazy amounts of energy back when I form my products, and so you end up seeing a reaction graph that looks more like this. So here are my reactants. Once again, maybe not a bad thing to label. Here's your activation energy, right? Huge peak that I have to get up and over. And here's what I get back when I make my products, which isn't a whole lot. So maybe I made that bad investment, right? If we go back to that analogy, I paid $200 for some sort of product, was only able to turn around and sell it for $100, and so I ended up netting a loss of $100. Problem is that a lot of this is what we see in metabolism processes going on in cells, and so we'll talk about enzymes later in this unit, and they're going to be a big help in ensuring that all of these endothermic reactions that we need to happen, otherwise life kind of stops, they're going to help us get over that activation energy hump a little bit easier. Last thing I wanted to point out about chemical reactions. So remember when we started today, I said check out your arrows. Your arrows always point to your products. Well, there are situations where I've got chemical reactions that can actually happen in both directions. We talk about them as reversible reactions. And assuming that this side is going at the same rate and making this product as this is making these as products, we talk about that chemical reaction being in chemical equilibrium. And so you'll see these double-headed arrows or two arrows stacked on top of each other. And all that's indicating is that the reaction can happen in both ways. So if I were to dump some excess CO2 in here, it would push this and make this more often. If I were to remove H2O from this side, then this side would happen a little stronger until they were making each other at the same rate, which is that idea of chemical equilibrium. So lots of things that are going on in living systems tend to go both ways depending on the concentrations that are present at the time. And it's a good way for your body to sort of help maintain its homeostasis.